last session of this morning. This is the only session of the program where you don't know what will happen next. So be very attentive what will happen. And after all, please do your questions. Once again, no more than 5 or 6 questions for each member of the staff here. I will start with the first presentation. The first presentation will be on the influence of PREHYDROLYSIS KRAFT conditions on pulp FOCK reactivity. This presentation will be made by Mr. André Cunha. Here we go. I will do a short presentation. Mr. André Cunha is currently pursuing a PhD in chemistry at the University of Beira Interior in Portugal. He earned his bachelor degree in biotechnology and completed his master degree also in biotechnology at the same institution. During his master's programs, his research was primarily centered around microalgal metabolites, especially chlorophyll and lipids. In his current PhD studies, André research is focused on dissolving pulp production and wood biorefinery, with a strong emphasis on recovering high-value compounds for secondary streams. So, André, the floor is yours.
Thank you for the presentation. It's a pleasure to be here. I will try to be fast. People may be hungry, and I have still 2 poster presentation. So, this is a side project of my PhD, where we are studying the production of dissolving pulp by the PREHYDROLYSIS KRAFT method. These are the co-workers, and my orientator is Professor Dr. Rogério Simões. So this is the poster. I will do a bit more of in-depth introduction of the project and the results, mainly the results. So dissolving pulp is a raw material, I would call it raw material, to produce regenerated cellulose. These are the 2 types of raw materials that can be used to produce regenerated cellulose. On the right side, we have cotton linters. There's a high purity cellulose fibers already in this case, and it needs less chemical treatments than when compared with the wood pulp. However, the textile market is increasing, and there's a difficult upscale regarding cotton linters, maybe because of the use of insecticides and water consumption. On the other side, we have the wood pulp. Already talked a lot in this event, so we require higher chemical treatments. However, we have advantages that we are exploring. The dissolving pulp by the PREHYDROLYSIS KRAFT is the objective study of my PhD. We already have some studies about the valorization of hemicellulose removed during the PREHYDROLYSIS, and I will also present later the valorization of lignin. The objective is to produce a cellulose fiber with high cellulose content, and already talked before. We have specific conditions to produce a good quality dissolving pulp, such as the intrinsic viscosity that was shown in the other room, the importance of this parameter to dissolve it. The kappa number must be low, alpha cellulose must be higher, and it's important to have a low metal content, focusing on the recyclability of the solvent used to dissolve the pulp. So we are working a bit in the viscose process, where we use disulfide carbon to dissolve and to produce the dope of the fibers. The dope is then, by electrospinning, for example, regenerated and washed in the later phase. So regarding the methods, we can split this work in 2 parts. The first study, we studied the flow-through PREHYDROLYSIS KRAFT pulp. It's the scheme represented. In this case, we As I said before, my PhD focused on the PREHYDROLYSIS craft, and this is a previous work where we studied the valorization of the hemicellulose removed during the PREHYDROLYSIS. With this method, we were capable to control the solution, the pH of the solution used, the flow of the solution in the reactor, and the temperature of the reactor. This pulp will be compared with the standard batch PREHYDROLYSIS shown in the right. The other part of the project, we worked with recycled pulp. There's a pulp in the end of the life of utility. It has specific characteristics that are more difficult to work with. Both pulps, we did the KRAFT cooking in the batch system, so the only difference is the PREHYDROLYSIS reactor. Regarding characterization, as I mentioned before, it's important to follow the viscosity of the pulps. We also studied the composition of the pulps, and we did the FOCK test. FOCK test is a mini scale of the viscose process. So, starting with the hemicellulose and lignin removal. In the first part of the graphic, we have the results from the recycled pulp. We can see that with the treatment, the PREHYDROLYSIS in the KRAFT cooking applied in the recycled pulp, we have a decrease in the compounds that are not wanted in the dissolving pulp. However, they are still far away from the commercial dissolving pulp. When comparing the flow-through and the batch system employed in the PREHYDROLYSIS sequence, we can see that the flow-through reactor has produced pulps with higher cellulose content. That was one of the objectives and one of the interesting results of employing this PREHYDROLYSIS. Regarding intrinsic viscosity, we can see that the treatment employed in the recycled pulp decreased the value to the quality, to pulps with a better quality, aiming for dissolving pulp, so between 350 to 600. And the PREHYDROLYSIS KRAFT with the flow-through reactor also reduced the intrinsic viscosity to the values of optimum to produce dissolving pulp. Regarding reactivity, we have interesting results, particularly when studying the recycled pulp. We can see that we almost twofolded the FOCK reactivity of this pulp when employing the two chemical treatments. One of the interesting points is that we cannot remove a lot of hemicellulose in this process due to the characteristics of this pulp. However, due to reduced viscosity, we have this increase in reactivity. Regarding the flow-through, as we seen before, it's a pulp with higher purity, and this translates in a higher reactivity. They're still a bit far away from the dissolving pulp commercial, but it's a method we need to optimize. And this is the future works enter. So one of the interesting results was the increase in FOCK reactivity in the recycled pulp, so we can produce pulp from an end-of-life pulp with, we can enter the circular economy with this type of pulp. Regarding the future works, we'll try to individualize the different pulp characteristics, such as kappa number, crystallinity, porosity, surface area, that can impact the FOCK reactivity, and we'll try to individualize the different aspects of it. Just to finish, I would like to thank Biotech for the financing of the project, and Professor Rogério for the orientation, and Professor Álvaro for the work about this project. Thank you for your attention.
Okay. Thank you, André, for your presentation. We will now move immediately to the second presentation. The It will be alternative for non-wood fiber for packaging application and evaluation of ammonium sulfate, a reputational pulping method for corrugating medium and liner. The presentation will be made by Mr. Jorge Franco. I will give a brief presentation for him. Mr. Jorge Franco is an experienced chemist and doctoral student specializing in forest biomaterials at North Carolina State University with a 12-year track record in the pulp and paper industry. He held roles as a chemical recovery plant process engineer, technical support chemist, and analyst at Smurfit Kappa, Colombia. He has an expertise in coordinating ISO 70025 and ISO 1401, so quality and environmental standards, leading the implementation of oversight of laboratory standards, metrological control, management, and process improvement. So, João, the floor is yours.
Thank you so much. Hello, everyone. First of all, I would like to say thank you to Tecnicelpa for having us here and to give us the opportunity to present this work. This work is called Alternative Non-Wood Fiber for Packaging Application. An alternative has an alternative process method to produce pulp for packaging applications such as corrugated medium and liner. I would like to mention also that we are working in NCSA through the consortium SAFI, which is the Sustainable and Alternative Fibers Initiative. So let's start. I'm going to go through the objectives. I'm going to give you a little review of the process. We are going to explain the methodology, the results, and the conclusions of this research. So basically, the objectives is evaluate the ammonium sulfide process, which is we have called semi-chemical process to be used on non-wood materials, such as wheat straw, miscanthus, and Swissgrass. With the two last are grasses that we can consider crops. So this is an important concept that we are using a no-sodium alternative process. I'm going to explain later why. So the second objective is to evaluate the mechanical properties of these fibers to be used in corrugated medium and liner manufacturing. And also, we want to evaluate the morphology of those fibers and what kind of a relationship has with the mechanical properties on these grades. So as a overall overview of the process, maybe you wonder why we are using ammonium sulfide on non-woods. And the reason is because we can integrate a more environmental friendly process for non-woods in a small scale. So what does it mean? So as a previous presentation, you might know that the sulfide can be used in a pulping process, and we can obtain a spent liquid to be used in different applications. So nowadays, we know that, for example, the spent liquid from the sulfide process could be used as solid amendment, or we can obtain more valued products such as lignosulfonate from this spent liquid. So basically, this is the idea. So as a methodology that we are using to evaluate this feedstock, we are using a systematic way to test these feedstocks. First of all, we did a pre-treatment of the feedstock. We did some hammer mill and screening. Then we applied different conditions for obtain the fibers, doing a pulping, using a systematic way, using 50% of the total SO2, a liquid wood ratio around 4 to 1, sorry, and using a temperature at 170, which are common process conditions to obtain pulp. So as you can see here, we are changing the cooking time, and we want to see what is the effect of the cooking time on those pulps. So then after pulping, we refine those pulps using 2 stages. And we evaluate the total yield, the kappa number. We also evaluate the refining of those pulps and fiber morphology. So because we are short in time, I would like to show just a quick summary of the result that we already got. So in this graph, you can see, for example, for wheat straw, in this graph, we are comparing, we are doing the comparison of the tensile index for common fibers or for conventional fibers such as OCC, which means all corrugated container board, and we also compare this property with softwood, which are common raw materials for liner and corrugated medium. And something that is interesting here is that when we change the cooking time, we can obtain similar properties than OCC and even close to softwood fibers. So it's important also to mention that maybe one concern is the drainability of those pulps in the paper machine, and we know that these properties depend on the refining. So in this study, we are considering like operating range in order to improve the properties by refining. So let's see what happened with miscanthus. We have seen here the same behavior, a little lower than the benchmark fibers, and for Swissgrass, we had seen lower properties than OCC. Which is interesting is we evaluate all properties, the main properties for corrugated medium and liner. We see that those fibers have the potential to be used at least in corrugated medium. So finally, we did like morphology analysis, and we realized that, for example, when we compare the coarseness value, which is a common measurement for fibers, we realize that there is a good correlation with several mechanical properties and the coarseness value. So, which is important because we can estimate, depending on the coarseness of those pulps, how is going to perform those properties on paper. So as a conclusion, we believe that by using ammonium sulfide to process these non-wood materials, we believe that there is a potential to be used in packaging, at least in container board application. Thank you so much.
Okay. Okay, we will now move on to the next speaker. The work to be presented will be optimization of the bleaching process, and the speaker will be Mr. Raphael Cota. Raphael is Brazilian. He's graduated in Control and Automation Engineering in Rio de Janeiro, and the equivalent for Master in Electrical and Computer Engineering with Automation specialization in Portugal. He has more than 8 years working in data analysis and development of automation techniques and multivariable APC advanced process control for the oil and gas and also pulp and paper industry. Recent projects developed focus on fiber line and recovery utilities areas in KRAFT pulp mills. currently living in Portugal and working for ANDRITZ in the project for ALTRI Helping Mill. So please, Raphael, go on.
Thank you for the presentation. Hi, my name is Raphael. I'm here for ANDRITZ, working as an OPP engineer, and I just would like to give you a quick start here. That's the ANDRITZ portfolio to help the customers on the journey of automation and digitalization. Here, ANDRITZ has products involving control system, computer vision, plant management, asset optimization, training, and what we are focusing today is the process optimization, with the main objective is maximize process performance. Here, what we are saying, the matrix is the ANDRITZ software we use, and the focus will be on the matrix OPP to optimize plant performance. Now going back to the project that we have developed in Selby Mill on the bleaching area. So here's a quick introduction of the bleaching. Here's a photo. And the layout of the bleaching at Selby with 4 bleaching stages, 2 with chlorine dioxide and 2 with hydrogen peroxide. They are intercalated stages, and the main objective of the bleaching, like almost everyone knows here, is to gradually increase the brightness of the pulp among those stages and reaching the final set point to send it to the drying machine. Here, that's the method to optimize the bleaching performance. We developed 8 APCs. The focus of the APCs are the bleaching, the brightness, and the pH on each stage. We have 4 stages, so 1 pH control APC and 1 brightness control for each one of the stages. The main focus is to keep the quality. The quality is the target of each stage brightness. And beside that, we have to optimize chemical consumption and optimize the chemical reaction efficiency. For the contours here, for the brightness contours, we consider a set point that's actually now it's sent by the operators of the area. We consider the brightness measurement. We consider the measurement on the previous stages. Like if we had some disturbance on the previous stage, we have to compensate it on the next stage. We consider stage production, pulp constants, and the concentration of the chemical that is used for each stage. Our outlets of our contours are the specific dosage of the chemical used on the current state and the flow of the chemical. For the pH states, we consider the set point provided by operators and the pH measurements, the stage production, also the pulp consistency, the concentration of the pH chemical, and the outputs will be the specific dosage and also the pH chemical flow. So that's a MIMO APC. It's based on MPCs, a MIMO control based on MPC with some feed-forward strategies, and we also use some lower strategies to deal with singularities of the mill. Results on our control was a more stable brightness at the end of each stage, and mainly at the final pulp. Like I said before, the main objective of the control is to keep the quality. Keep the quality, reach the final set point, and reach the target of the mill brightness. So, with a more stable brightness, let's say we have a reduction of 27% on the standard deviation on the final pulp brightness with the 8 APCs developed in the mill. Well, another big benefit is to automatically deal with daily process disturbance. Operators are there to help, but the control is also there to help their daily routines. Considering the chemical consumption, we have a reduction of almost 5% on chlorine dioxide, near 12% on peroxide, and 15% on caustic soda. What I have to to add here is that bleaching is after the cooking process. So the cooking process and the cooking condition, like the kappa number and the brightness of the pulp that is going to the bleaching, those are important variables, and those will totally be related with our results. That's a quick overview of the project we have developed. I also would like to thank you for Selby Process Engineer for their participate in the process. And I also would like to, not only the process engineer, but operators, all the Selby team, and everyone that make the work to be done and the work to happen. Thank you.
Thank you for your presentation. We have a different situation now. There is someone here that deserves a second opportunity. So I will call André again, because he deserves a second opportunity to present a new poster. It's KRAFT LIGNIN Polymerization by LACCASE, and I will not present him again, of course. Okay, please, André.
Thank you again for the presentation. So as I mentioned before, we studied the valorization of the secondary streams of the pre-hydrolysis KRAFT cooking. In this project, we will study more the lignin case. Following the same method, I will give a bit more in-depth concepts about the introduction of this project and the results. As we've seen, lignin it will be a pathway to increase the biorefinery concept in our industry, in the paper and pulp industry. It belongs to the three pillars of sustainability, such as the environmental, the social, and the economic. One of the things that we want to improve is only 1 to 2% of lignin produced is converted to added value compounds. It's a low number that we want to increase. So where can we find lignin? Lignin is produced in the cell wall, and it's based on the three monomers, namely coumaryl, cuniferyl, and synapyl alcohol. In the plant cell wall, the enzymes LACCASE and peroxidase will oxidize these compounds, the hydroxyl compounds, and will produce radicals. By the interlink between the different radicals, the famous lignin structure will be produced. However, in the paper and pulp industry, we don't want it in the main product, the cellulose fiber, so we need to remove it. There's a wide variety of techniques to remove it, such as KRAFT cooking, soda cooking, sulfite, ionic liquid, there's a lot. In this work, we'll study the removal with the soda cooking, mainly due to the non-existence of sulfites in the lignin removed by this process. So lignin can be evaluated by further fragmentation. It can be a source of different compounds that can be applied to produce polyesters, such as phenol, toluene, benzene. There's a lot of compounds that we can proceed and valorize from lignin. However, in this work, we see lignin as a polymer. Based on the natural function of lignin in the cell wall, we want to replicate it in composites, for example. So we have lignin, we dissolve it and we fragment it, and then we need to repolymerize it to achieve this function. For this means, the method that we applied, based on also my PhD project, we studied the PREHYDROLYSIS, in this case of soda cooking of Eucalyptus globulus wood chips. We did the PREHYDROLYSIS to achieve a lignin with less contaminants, like the sugars from the hemicellulose. As I mentioned before, the soda extraction will allow us to work with the lignin with better characteristics for the aim of this work. This lignin can also be fractured. Yes, we can also do a solvent fraction of this lignin to achieve different groups of the raw material lignin. In this work, we also studied 2 different LACCASEs, one with better reaction at pH, high pH, and one in the pH 5 that will compare the results. Regarding the characterization, so we analyzed the molecular rate distribution to analyze if the lignin is polymerized or there's a decrease or increase in the molecular rate distribution. We also analyzed the lignin conversion, so we filter the solution after the treatment and we analyze how much material is withheld in the filter, and we also studied the phenolic content. I will show more about the phenolic content, but it measures the hydroxyl groups that are available for the reaction. I will start with the molecular rate distribution between 2 different treatments with 2 different LACCASEs. The main difference is when we apply the bacterial-based LACCASE with higher pH, we can see that the lignin peak is inferior with the treated time. By this means, we have a lignin with higher molecular rate, showing the polymerization. So the next step was to study why. Why we have different behaviors for LACCASE. What we see is we can start by the peak size, the signal of the method that we studied. We can see that the lignin in pH 5 has inferior solubility. By this means is less reactive for the treatment employed. On the other side, we have higher solubility in high pH. These results go in concord with the filter measurement, where we can see that the inferior pH used, we have higher lignin start from the 0 reaction time. As I mentioned before, one of the main difference is the retention time of the lignin peak, and we can see that in the bacterial LACCASE we have a decrease of it, representing the increase in molecular rate. So we have decided to go for this lignin. So the next step was to evaluate how the different substrates interact with the enzyme. So we studied, we call it the black liquor, but it's from the soda extraction at different concentrations, 1 lignin gram per liter and higher concentration. We also studied the fraction that is soluble in ethanol, and we also studied the PREHYDROLYSIS lignin that it is different. The molecular rate is inferior, and in theory it should be more reactive, but due to sugar contaminants, we didn't see those results. One more point about this table is the comparison between the direct treatment of black liquor at 1 gram per liter and the fraction that is soluble in ethanol. So, in theory, we think that the ethanol soluble lignin is a more pure, more purified, more clear lignin. However, the reactivity with the enzyme is inferior. And this is because of the fraction method that we used. We solubilize lignin in isopropanol, ethanol, and methanol. And the more reactive fraction of lignin is soluble in isopropanol. So we removed the higher reactivity lignin. However, we studied the soluble ethanol because it covers 50% of the raw material. Regarding the phenolic content, as I mentioned before, it analyzed the hydroxyl groups of our material. And we can see that with the treatment time, it has a decrease. By this means with the LACCASE treatment, we achieve denser structures and higher molecular rate. The figures is just a more visible example of the polymerization that we achieve. To summarize, we studied 2 different LACCASE. We achieve a better results with the bacteria alkaline-based LACCASE. We also studied the use of different substrates of lignin, and the further works will pass by the find applications for these polymerized lignin in composites. Thank you again for your attention.
Okay. So our last part of the presentation will be the production of polymer composites using lignin obtained by high-yield wood extraction with green solvents, and it will be made by Professor José Gamelas. He is a member of the Chemical Process Engineering and Forest Products Research Center since 2008. His recent research has been focused on paper-making topics, biomass fractionation and lignin valorization, nanocellulose, and nanocellulose-based films for packaging and old document restoration. He was included in this area of research in the list of the world's top 2% scientists in 2022, released by the Elsevier editorial group. So please go on.
Thank you very much for your presentation, and thanks for the audience as well. I will present a work related with the production of polymer composites using lignin obtained by high-yield wood extraction with green solvents. The objectives of this work were valorization of the wood of an invasive tree species. In particular, we have valorized Acacia delbata, extraction and isolation of lignins with high purity and yield from wood, using an approach employing green solvents, particularly ionic liquids and diepathetic solvents. Valorization of lignins by transforming them into other value-added products. Use of lignins in production of composites with other biodegradable polymers, and in particular, use of lignins in production of composites with polybutylene adipate terephthalate, promising polymer for plastic production with good biodegradability properties, aiming at improving mechanical performance and reduce costs. The experimental part comprised two sections. The first was the lignin extraction and isolation from wood. The lignin extraction and isolation had two main steps. First, it was the extraction using ionic liquid or diepathetic solvent of the lignin from wood that enable a first fraction, which is cellulose-rich material, and a dissolved fraction, which contained lignin, and from the dissolved fraction, after adding water, we could precipitate easily the lignin-rich material. So it was used an ionic liquid, which was butyl-methylimidazole methyl sulfate, mixed with water in the proportion of 4:1, and it was used as a azetic solvent, choline chloride imidazole solvent. The extraction with diepathetic solvent required higher temperature, but afforded a more selective extraction of lignin. The conditions for extraction of lignin were optimized from a previous published work. The second part of the experimental section is the preparation of composites with PBAT lignin. The structure of PBAT corresponds to polybutylene adipate terephthalate, can be seen in the picture. PBAT is a polyester, is a copolymer of butanediol with adipic acid and terephthalic acid. So it has one aromatic part, as you can see, and has one aliphatic part. And the aromatic part obviously could anticipate a good compatibility with lignin. These composites of PBAT lignin were obtained by extrusion plus injection molding. It was prepared mixtures with 10, 20, and 30% of lignin. The composites were prepared with, were shaped in the dog bone format, as you can see in the figure. So it is, this format can be obtained by the injection molding we have used in the process. As for the results, I don't have too much time, so I will speak just of a few results. I will not extend too much into the results. I will speak about some results of lignin extraction and isolation. Here in the table you can see the yield and chemical composition of the lignins precipitated from acacia delbata wood. You can see yields of lignin recover close to 100% when using more severe conditions of lignin extraction. When using less severe conditions of extraction, lignin yields were in the range of 70 to 80%. As for the purity, the isolated lignin show total lignin values between around 83 and 93%, revealing high purity lignins, you can say. The analysis of polysaccharides revealed only vestigial contents less than 1% in the isolated lignins. So we have obtained lignins with high yield and high purity. These are only a few results as thermal stability of the lignins. There are other characterization data of the lignins, but I will only present a few data. Thermal stability is important, especially if you are going to make composites with other polymers. Here, there is another lignin. In the pictures, you can see the lignins obtained by extraction with ionic liquid, the lignins obtained by extraction with epitaxial solvent, and you can see another lignin. It is a KRAFT lignin. This lignin was our reference. How we obtain this lignin? We have performed a cooking of acacia delbata up to a kappa level of around 16, and from the black liquor of this KRAFT cooking of acacia, we have obtained lignin by precipitation with acid. So this is our reference, the acacia KRAFT lignin, and as I will show later, it can also be a good approach for the valorization of lignin. But returning to thermal stability, you can see that the lignins obtained by extraction with ionic liquid present higher thermal stability than the acacia KRAFT lignin. Okay. Acacia KRAFT lignin, it was a lignin obtained from the same wood sample, okay, but based on the KRAFT cooking process. The ionic liquid lignins also show an increase in thermal stability with increase in severity of treatment conditions. So if you use higher temperatures and higher reaction, higher extraction times, you can obtain lignins more thermally stable. As for the lignins extracted with eutectic solvent, these show lower thermal stability than the ionic liquid lignins, but again, more severe conditions of lignin extraction also conduct to better thermal stability of the recovered lignins. The most important of this presentation, I think it's the results for the composites of PBAT lignin. I just show, once again, only the mechanical properties. There are other data, but I don't have time to show these results here. As for the mechanical properties, we can see the variation of tensile strength and the elongation break with lignin percentage in composite up to from 0 without lignin, only PBAT, up to 30% of lignin. You can see in the left, in the figure of the left, that the tensile strength decreases, okay, not very much, but it decreases, and then from 20 to 30% almost reaches a plateau, and sometimes it can even show a slight increase. As for the elongation at break, the elongation break is reduced up to 20%, and from 20 to 30% is almost the same. Elongation at break of PBAT is very high, so don't, this is really real. It's like this behaves. This polymer is very ductile, has an elongation break of 600%. So even if decrease the elongation break, the final values of elongation break are not so bad at all. Okay? So you have lower tensile strength and lower elongation break with lignin incorporation in the composites with PBAT. As for the Young's models increases. You can see also the results for acacia KRAFT lignin. It increases more or less steadily up to 30%. This was our objective because we want to improve stiffness of the PBAT. PBAT is a polymer, is much used in applications like shopping bags, like food packages, like agriculture films, but it has low stiffness. So our idea was to improve stiffness. One of our objectives was to improve stiffness of the composites. So we have achieved this objective. We can see that stiffness is improved. The Young's models for PBAT alone is around 60, 70 megapascal, and for mixers with 30% of linen, we have Young's models up to 150 megapascal. Although the best results were obtained with linen extracted with eutectic solvent, result with ACACE KRAFT linen is also good. So it can also be an interesting option. Final conclusions. It was possible to obtain high purity linens with more than 90% of purity from the wood of Acacia delbata, with yields of linen recovery approaching 100%, using either ionic liquid or deep eutectic solvents for the extraction of linen, followed by the precipitation of linen with water. So it is good, good results. Some of the linens were more thermally stable than the KRAFT linen obtained from the black liquor of Acacia delbata, cooking. However, it is not to say that the KRAFT linen is worse, but it's a result. As you can see, Acacia KRAFT linen is also a good option. When linens were used in production of composites with PBAT, we have obtained lower elongation break and higher Young's models, values, compared to PBAT alone, which means that the stiffness was improved with the linen incorporation in the materials. Finally, it's not here, but about the conclusions, we can say that if for the PBAT, for the particular case of PBAT, linen seems to see a good approach to improve some of mechanical properties and eventually to reduce costs, because we are talking about a subproduct of the pulp production that most of the amount is burned. The acknowledgements are to the Chemical Process Engineering and Forest Products Research Center and to REACH, where the cooking of Acacia delbata was carried out. Thank you very much for your patience.
Okay, thank you for all the speakers. We are a little bit out of time, but I will open the floor for a few questions from the audience. Please do your best. I will not give you too much time to think about lunch, because I will give you just a few seconds to think about it. Okay. So I have just a few fast questions from the speakers here with me. And I will start with André, and just a very simple question. Why reactivity? Why do you focus first on reactivity? Why is that so important?
So, regarding dissolving pulps, there's a problem with reactivity. So, it's a method that we use to evaluate the quality of the dissolving pulp, and in this case, we follow the viscose process. It's a method that allows us to focus on the dissolving properties of this type of pulp. It's a result of different conditions, but it summarizes the quality of the dissolving pulp.
Okay. Thank you. Just a question for Jorge. You talk about the utilization of ammonium sulfate as a pulping method, but when you talk about new methodologies, we always wonder about how to close the cycle for this kind of new approaches to be useful in an industrial approach. So can you speak a little bit about that?
Thank you for the question. So basically, when we think in non-woods, we have to think how to deal with the spent liquor. So if we think in, for example, in wheat straw, we know that wheat straw has a lot amount of silica. So saying that silica can be a problem in our recovery processes. So if we think in a soda process, should be the same problem. So when we think in our process using ammonium sulfide, our proposal is to recover the lignin sulfonate as a side product, as a value add product. So in that case, if we use the spent liquor as a soil amendment kind of fertilizer, we can use that product to grow crops and then use those crops into the paper products. Exactly.
Okay. Thank you for your answer. Now a question for Raphael. And I will do a provocative question for you. So you talk about process optimization. You talk about less variability on the process. You talk about something automatic that is changing the process in the sense of less variability. The provocative question for you is, how far can we go? Can we get to a point where this kind of automation can run the process by itself?
That's a good question. But let's say, I think we are on that journey. We are going for an autonomous mill, an autonomous operation, but we are, let's say, we are starting this journey. Now, we still need operators, we still need to trust on the measurements we have on the field to make sure that they will work perfectly every day, every hour, every minute. So that's I think that's the most important for now. But to keep going on this journey to an autonomous mill, we have to go step by step, and but it will be possible in the future. Yeah, I definitely trust that. And like I said, previously I worked a little on oil and gas industry. And for the oil and gas industry, they already have some, let's say, some kind of operations autonomous. Not too complex ones, but they have some.
Thank you. My final question for Professor José Gamelas. You talk about extraction, so solvent extraction with ionic liquid and the dipiothetic solvent. A tricky question for you. Okay, regardless of the efficiency of this process, you are using solvents that are or quite expensive or difficult to synthesize. So do you think that can be an evolution for this process to become industrially applied in the medium to large term?
First, separate ionic liquids and dipiothetic solvents. The price of ionic liquids is really high, so I would discard maybe ionic liquids. But as for the dipiothetic solvents, they are not so expensive, and there is a possibility of reuse, and they are easy to prepare. So it could be a good option. In the future, we can. This was from imidazole, choline chloride, but they can be produced from urea, not so expensive materials. But I would like to note that the work also showed that we can use a KRAFT linen from acacia cooking. And the results are not so different from the linens obtained following ionic liquid and hypothetic solvent extraction. So, and this was, I think, in this case it is easier because you only have to take the black liquor and precipitate linen by adding acid, and that's what we did. We just did that. We took the black liquor and precipitate linen by adding acid, and this was done with acacia, but it could be done with eucalyptus. KRAFT cooking of eucalyptus, you could also, from the black liquor, could also precipitate linen and use this linen to produce this kind of composites. Because this work, first, our interest was on the ionic liquid and hypothetic solvent extractions because it was a sequence of an older work. But we also found that maybe you don't need the euthetic solvents and hypothetic solvents and ionic liquids, and use just linen from KRAFT cooking, and it works.
Thank you for your answer. Before I let you go, just two information. So, from now we will have it's lunchtime between now and 14. So please come back here at 14 for the next plenary section with Mr. Ronaldo Gonzalez. And please, an applause for the speakers.